Hello, welcome back to my channel. My name is Suno Ash, and now in this video we're going to look at length of a vector. Good. So in our previous video we introduced the vectors and how to represent a vector, right? Okay, great. So I hope you watched that. If you didn't, you may have to go back over there just to get the basic understanding. Good. Now we're going to learn how to find the length of any vector. So we talked about vectors being in 2D and 3D, that is vectors in R2 and R3. So we're going to learn how to find the length of each of those vectors. So we start off with 2D. So let me just put it here as number 1. So if the vector is in 2 dimensions, right? Good. Okay, so what do we mean by the length of a vector? Well, we know vectors to be physical quantities that have both magnitude and direction. So the magnitude is the length, which is another way of saying the size of a vector. Now, vectors are represented, since vectors are more like abstract, as a result of abstractions, okay, we use line segments to represent them. That is directed line segments, so that they have direction and those lines have measures. So the measurement of the vector is the length of that vector, which is what we call the magnitude of the vector. Good. Okay, so let's suppose, so I'm going to use SPS for suppose, we have our vector here in 2D. So let's say vector V is a vector in 2 dimensions, that is AB, where A and B are real numbers. Okay, so we want to find the length. So I will say we want to find the length of vector V. Now, to find the length of a vector, we use this notation. That is the norm. That is double bars over here, double bars over here, then the vector between. So this is read as the magnitude of that vector, or the module of the vector. Okay, so we want to find that. First thing we want to do is to represent this vector. So I'm going to assume, without loss of generality, that A and B are both positive. This doesn't really mean anything. Okay, so this is what we'll do to represent this vector. Given that it has only 2 components, so I'm going to use the Cartesian plane. Sorry, let me bring this down a little bit. Since A and B are both greater than 0, okay. So that's why I made the assumption. So maybe let's think about this point as A. Maybe let's think about this as B. So this first entry is going to be in the I direction, which is in the X component. That is the unit vector I direction. And then this is the unit vector J direction, which is the Y direction. That is the Y axis. So given that, we can trace A and B to where they will meet, and it's going to be somewhere here. So these 2 coordinate points will meet there. So we can take our vector as a position vector from the origin to that point. So let me make the line nice enough. So to be from here to here, something like that. Good. So that is a vector, position vector V, which we represent as that. So maybe something like this. Good. Okay, so that's the vector. Now we want to find the length of that vector. So what we simply do is to construct this line so that it moves from there to the x-axis, right? Okay, so if we have that kind of line, we can think about this as a right-angled triangle, where we have the other 2 sides and then the hypotenuse side. So the hypotenuse side will be the length of vector V. Good. So using the notation, I will say the length of vector V will be, that's the length of vector V. Now to find the hypotenuse side by Pythagoras theorem, we say that the square of the hypotenuse side is the sum of the squares of the other 2 sides. We know that from here to here is measured as A, and then from here to here is, from here to here is measured as B, from here to here is measured as A. That means we're going to have this to be the square root of A squared plus B squared. So this right here is the length of vector V, where V is given as the vector components A and B. So what you just have to do is just take the square of the X component and then the square of the B component, sum the squares together, and then take the square root of the result. Okay, that's nice. Now, that is just if it is in 2 dimensions. What happens if the vector is in 3 dimensions? Like if it's a vector in 3D. So let's look at that. So, sorry, I wanted to say case 2, not number 3. Case 2. If the vector is in 3D, that is to say vector in R3. Good. So let's suppose we have a vector W to be the vector in R3, and it is given by A, B, and C. Good. So the first thing we want to do is to represent this vector. But the process, this is what I'm going to do. I'm going to let this happen. I'm going to let vector v, which we've discussed already, to be a vector in 3D, but it has this component a, b, 0. Now let me explain. So looking at this, we say v should be ab, right? But here I'm calling it that same v to be ab, 0. So what am I really saying? Now in our previous video, when we learned how to represent a vector in 3D, we saw that this z component was responsible for the height. That is, how much the vector is shooting up from the origin, okay, in the pointing in this direction. So you see, it's shooting up 1 unit above the xy plane. That is because the z component there is 1. So in a situation where the z component is 0, it means that this vector will not shoot up. In other words, this vector will lie exactly on the xy plane, which is what we have right here. Good. Okay, maybe let's just go ahead and represent that to be clearer if it is not clear at this point. So let's see what we do. We just get our 3 axes, the z axis, the y axis, and then the x axis. Okay, so that's what I'll do first. So let's call that the z axis, this is the y axis, and then this is our x axis. So that is pointing the direction of unit vector I, unit vector j, and then unit vector k. Good. So maybe let's think about this for vector w. Let's think about this as a. Let's take somewhere here as b. I'm not going to write it down because it's going to interfere with the work. Then maybe let's take this as c. That's relation to vector w, right? Good. Maybe let's start off by representing vector v. So vector v has a, b, and then 0. So we look at a in the x component, we trace it the way we meet b in the y component. So those 2 vectors will meet somewhere here, and here, right? So we can draw a line segment to show that as a position vector from the origin up to that. So we have that to be our vector v. Good. So represented in blue like before. Now to represent vector w, it is not really hard from here. So from what I explained, this is exactly on the xy plane because the z component is 0. In other words, this thing is not shooting up by any unit. For a situation where the z component becomes c, it means it's going to shoot up by c units. That is to say, it will have a height of c units above the xy plane. So vector w should be something like that. So we call this vector w, where this length from here to here is c units. So you see above the xy plane. Okay, so let's say we try to join these two. We try to join this to that. Okay, so yeah, good. So this is vector v. This is, maybe I can think about this as another vector having only c entry. The other entries will be 0, then that's vector w. So maybe let me do that. So from here I can say we can split vector w into this. We can write vector w as vector v plus the vector containing c only. So I'm going to say vector like this 0, 0, c. So what is going on there? Oh, I needed to use green for that. Excuse me. Okay, so let me write it again. 0, 0, c. So let me express this. Now I know we've not done addition of vectors first. We've not done it yet, but we'll do that. So there's nothing wrong with that. We'll do it, but it's very simple to think about. In fact, we'll learn right here. So this is what I'll do. Vector v, from what we've written out here, is just the vector containing a, b, and 0. So if we add it to a vector containing 0, 0, c, 0, 0, c. So what we're going to have, of course. Now, in addition of vectors, what we do is that we add them component-wise. So you add a to, that is, you add the vector in the first entry to the vector in the first, to the component, to the first entry of the second vector, second entry of the first vector, second entry of the second vector, then third entry of the first vector, third entry of the second vector. That is to say, you're going to say a plus 0 is a, b plus this second 0 is b, then this 0 plus c is C. Good. So that gives us the vector W we started off with. Okay, I just wanted to show that, but we don't really need it here. So I wanted to show that we can write vector W as this. That is the sum of these two vectors. That is to say, if it's a vector V plus this vector, if you think about this as a vector containing only C, we will get from here to here. That's how addition of vectors should be thought of. Now, there is an important thing to know, that this vector V and this green vector containing C are perpendicular to each other. Okay, with time we will get to verify that, but you just have to believe me, right? Perpendicular to each other. In fact, if you've read up some properties of dot products, you know that when two vectors are perpendicular to each other, their dot product will be 0. So if you take the dot product of this and this, you get 0. Now, why is it important for them to be perpendicular to each other? It's important because if they're perpendicular to each other, we can apply the Pythagorean theorem. Just like before, this line is perpendicular to this, so we are able to apply the Pythagorean theorem. So, having said that, to apply the Pythagorean theorem on this to find the length of vector W, we'll have to say length of vector W, which we know the notation to be. Now, of course, by Pythagorean theorem, we need to say the square of the hypotenuse side is equals to the sum of squares of the other two sides. So I'm going to have to be careful with this. I'm going to say the length of this vector plus the length of this other vector, which will be the length of the vector containing only C, that is 0, 0, C. Good. Okay, so that is the sum of the squares of these other two vectors. So that's how to think about it. So we can say the length of vector W will now be the square root of this other one. But what is the length of vector V? We've done that earlier when we found the length of vector in 2D. We know that to be the square root of A squared plus B squared. So I'm going to substitute just that. And we're going to have this to be the square root of A squared plus B squared. Alright? But then this has been squared. So I'm going to square it. Okay, I'm going to add it with, well, what's the length of this other vector? What the length of a vector containing only one component is just that one component squared. This is just like saying from 0 to C, you just C. It's simple. Look at this. You just see the distance from here to here is C. So that's why I just say the length of that vector is just C, and then you square it because of this square out here. But then I've taken away this square, which means I'm going to introduce the square root on this right hand side. Okay, great. Now let's see what this will give us. Well, you can work this out. It's very simple from here. This square will cancel out with this square root because the length has to be positive, leaving us with A squared plus B squared plus C squared. Okay, so you see the length of vector W, which is in 3D, is just the square of A plus the square of B plus the square of C. And you can also observe when we had a vector in 2D, which is AB, the length was square root of A squared plus B squared. So with those two results, that's with the observations, we can generalize. That is to say, in general, if given a vector, let me use vector U, okay? So given a vector U, which is a vector in Rn, that is to say, we can represent U as a vector whose components are U1, U2, up to n of them, right? So the dimension determines the number of entries a vector has. So up to n of them, I wrote 3. What's wrong with me? Let's just clean it up and write what we meant. That's n of them from 1 to n. Then the length of vector U is going to be the square root of the sum of squares of this component, U1 squared plus U2 squared, all the way up to UN squared. That's it, alright? That's it. Good. That's the generalization of that. So in the next video, we're going to do some examples of how to find the length of some given vectors. Okay, so I love this general result, right? Okay, thanks for watching. I hope you enjoyed the video. Please don't forget to subscribe to my channel, and we'll continue from my next video. Please, this is like this. Alright.